Yesterday we mentioned the logistic curve. So today I wanted to just go a little bit more in depth on how to read one and understand what it's telling you. All right, why logistic growth? So logistic growth is a math function. Like exponential growth is a math function, logarithmic growth is a math function, and logistic growth is a math function. What a logistic graph looks like is this, sort of looks like this letter S. So when we talked about exponential growth, exponential growth that we looked at was like that. Okay, a logarithmic growth, if something was growing logarithmically, okay, if we connected the dots and it gave us this shape, this is a logarithmic curve. All right, so this is exponential. So something like a to the x. Okay, this is a logarithmic curve. So y equals log, let's say x. And then you have what's called logistic growth, which is sort of a combination of the two. And logistic curves look like this letter S here. It's a combination of when something is growing exponentially, so that means it's growing really fast at the beginning, but starts to decrease, the growth decreases at a later stage. It's still growing, it's just not growing as fast until it reaches some sort of maximum. So in terms of a virus, that maximum could be the total number of people in an area, because if everybody is sick, or eventually everyone would be either sick or immune, the growth would have to start slowing down. So that's the three different types of growth that we've looked at so far: exponential, logarithmic, and now this last type is logistic. Now, you've seen this growth before, probably in a science class if you were learning about population. All right, a population will grow exponentially until the population becomes large enough that the carrying capacity of the environment starts to slow down the growth. Typically that involves resources, especially like food. All right, if the environment can't produce enough food to handle the size of the population growth is going to start to diminish. Now, some interesting facts about a logistic curve. When a curve is changing from exponential and then it starts to become logarithmic, so the combination of those two is logistic. The point where that happens is called the point of inflection. And what that does is that divides this curve into 4 parts. All right, the first part is it divides the time that it took to get to that point of inflection, and you can use that to predict when the curve would end. So for example, let's say that this was 0 and this was 10 hours. Let's say it was bacteria. And at 10 hours, that's when the point of inflection was. Well, we know that the growth would stop. If it took 10 hours to get to here, then it's going to take an additional 10 hours to get to here. So that's used in order to predict how long a pandemic could potentially last. All right, so let's say we were talking about a virus, and it took 120 days until the point of inflection was reached. Now, you can calculate this point of inflection several ways, but then the math involved is a little bit beyond what we're talking about today, but it has to do with finding the derivative at that point. And once the derivative is simply the slope of a tangent line, once that slope reaches a certain level, that, you know that the curve is going to start to tail off. So that's an application of derivatives, which is taught in calculus. So in terms of estimating how long a pandemic would last, using just this picture here, if we said it took 120 days to get to the point of inflection, well, that's half of the time. So the pandemic should last, and another, if it took 120 to get there, then at 240 days, pandemic would stop. That growth would stop because of what the point of inflection does. All right, it's also possible to use point of inflection to figure out or estimate how many people could potentially become infected. All right, so the other interesting fact is that this point of inflection divides the population into two halves. So prior to reaching the point of inflection would represent half the population, and then after the point of inflection, you would have the other half of the population. So what that means is, if up to this point 50 people were infected, then when it reaches this point, that's going to be approximately 100 people, because half of them are below, and then the other half is going to be above. So whatever this point is, or whatever this value is, if you double it, that'll give you a rough estimate of how many folks could potentially become infected. All right, and that's what we just talked about here. All right, so I'm going to show you that this is actually true, because we got two case studies. One is in Korea, from South Korea, and the other one is from Italy. And it's showing you, so this is the actual data from those two countries. And here's your logistic curve in green, right? And then the red vertical line, kind of like this dark red line here, that tells you where the point of inflection is. So wherever it crosses my graph, okay, wherever it crosses my logistic graph, that's the point of inflection. And if you can see, it divides the graph into equal parts. The amount of people up to this half below the line is the same as the amount of people above the line. So if you look at the number infected, it's at 4. Now that's 4 times 1,000, so that's 4,000. All right, and then you can see when the data was continued to be plotted, these white points are the actual data points from on these different dates. Okay, now when you're looking, by the way, when you look at these dates, okay, the rest of the world writes their dates differently. Okay, the month is in the middle, so that's February. That's the month. And then the date, sorry, this is February. And then the date is written out in front. So that's February 16th. So we would write it as 2/16. So then this is 2/23. All right. This is March the 1st, March the 8th, March the 15th, March the 22nd. All right? So the point of inflection being here, at that point there was about 4,000 infected. So we could use that. Once we knew that that was the point of inflection, then we would be able to predict that eventually there would be around 8,000. And if you can see, when the actual numbers were graphed here, these are the actual values, it reached 8,000. All right, now over to Italy. Here's the actual data on Italy in the white circles there. Okay, the point of inflection is right here where that vertical line crosses the graph, right? So at that point, there was 25. Now that's 25 times 1,000, so that's 25,000 infected, and that looks like it's around March the 10th. Okay, so somewhere between March the 10th and March the 20th, like maybe March the 15th, that's where it started to go from exponential growth to logistic growth. So if we go up to here and we see where it's leveled off, it should be about twice that, and it is pretty close at about 50,000. So this is using the point of inflection and showing you that using actual data, real-life data, that it can be used to estimate the total possible number of people that get infected. All right, so now what we're going to do is we're going to do this, and we're going to use it for Arizona. All right, so here's a model that I borrowed it from a professor in Vermont, and I adjusted the numbers to fit what the infections that we got in Arizona. So this is the actual data here from Arizona. Okay, these values here. So on the 8th of March, 5 cases. Okay, on April the 1st, 1,400 cases. So this data over here is based on the numbers I got from the Arizona Department of Health on their website. All right, so click on this model and it'll open up the model on GeoGebra. That looks like this. So here's how the prediction works. If you go down here where it says adjust the model, there's a little slide and you can drag on it. Okay, and it'll move the model along by days. All right, so what that does, and oh, before we do that, up here where these two little curls are, circles, if you click on that, you can reset the model. Okay, now I'm going to open up a window where it's a little bit more responsive. Just a moment. So here's our model once you've opened it. And what you're looking at here is that these gray points, those are representing the actual data points from the table over on the left. So these points right here are represented by, excuse me guys, sorry about that, jumping around, these points in red and then these other points in black. Now the points that are in red are being used to generate this logistic curve right here. All right, now here's where you're going to be looking. Here it says if the point of inflection had been March the 24th, then we could have predicted that the number of cases in Arizona would have been around 712, right? But unfortunately, at that point, that was not the point of inflection. So what we do over here is, as I take this slider and I start moving it out, it readjusts the logistic curve based on the point of inflection. So the date right here is March the 24th. Okay, if the point of inflection had occurred on March the 25th, then using this data, then we could have predicted that there would have been 803 cases. Okay, so if you slide this all the way out, you'll see the point of inflection keeps changing. It gives you the date, and then it tells you about how many cases there would be based on that point of inflection. All right, so if we keep going with our graph here, right, that's as far as we can go based on the information that we have up to Monday, 4/13. So based on that, if March 14th or March, if based on this data, if that allows us to predict a inflection point or to calculate an inflection point, not out to the 14th or the 13th, but back to the 4th, because you need so many data points before it and after it in order to be able to make this prediction. But we can predict out from that point of inflection on the 4th out to May 1st. So if indeed the point of inflection happened on April the 4th, then the number of cases would have, in the state, we could have estimated at 4,174. And that's using the fact that the point of inflection, which is right here, is around, you can see it's about 2,000 cases. So from that, you can actually predict out into the future that that would be our estimated total. Okay? So that would be if the point of inflection had occurred back on the 4th. Right? So that's one way that you can read a logistic curve, and you can use it to make estimates about what could potentially happen in the future. All right, you can go to the Google form, and there's just a couple of questions using this interactive graph. And take care, and I'll see you next time.